Okay, so in this video, we'll talk about eigenvalues and eigenvectors of n by n matrices. So in 4.1, actually, we made some short introduction to these concepts, and in 4.2, we studied how to compute determinants of any matrix, I mean, any n by n matrices. So now we'll get back to our topic that we have started in 4.1, that is eigenvalues and eigenvectors of n by n matrices. Okay, so now let's start with this kind of definition, or let's say the kind of summary. So the eigenvalues of a square matrix A are precisely the solution lambda of the equation, determinant of A minus lambda times I is equal to 0. And once again, why actually this determinant should be equal to 0? Because here we are talking about a homogeneous system, right? Here we have A minus lambda I, and here we have times, here we have vector X, and here we have 0 vector. Actually, it's not dot product, it's a matrix product here. And how did we get this? We got this from this equation. It's all about this eigenvalue problem. Here we have lambda X. Okay. So, and also for this system to have non-trivial solution, right, this determinant should be equal to 0, because if determinant is not equal to 0, then this A minus lambda I is invertible. If it is invertible, this homogeneous system has only trivial solution. Only the solution is 0 vector. But we are not interested in 0 vector. We are interested in non-zero vector that satisfies this equation. Anyway, so here, determinant of A minus lambda I, now we're going to call this characteristic polynomial of A. Why? Because if you just evaluate this determinant of A, this determinant of A minus lambda I, and we will have a kind of polynomial of lambda here. And here, if I just put here equal sign, equal and 0, that becomes an equation. And that is called characteristic equation of A. So now we added two more concepts, terminologies here. One is characteristic polynomial of matrix A, and the second one is characteristic equation of A. So now if you consider this example, here we have a 2 by 2 matrix whose entries are A, B, C, D, then it is characteristic polynomial. That is, we're talking about this characteristic polynomial, that is P of lambda. That is determinant of A minus lambda I. So now lambda I, we know that when you just subtract this thing from A, you're just subtracting lambda from all components or entries in the main diagonal of matrix A. So here we have A minus lambda, D minus lambda, D minus lambda. And if you just compute these determinants, here we have A minus lambda times D minus lambda minus B times C. Here we have B times C, which is equal to, if you simplify this, we have O lambda squared minus A plus D lambda plus AD minus BC. What is it? It's just simply a quadratic expression. So that thing is P of lambda is quadratic expression. So now if you just put here equal sign, it becomes quadratic equation. As you see here, if the matrix is 2 by 2, here we got a polynomial of degree 2. If it is 3 by 3, then we get here a polynomial of degree 3. If it is 4 by 4, we get a polynomial of degree 5, depending the size of the matrix. And of course, actually, when the degree is higher than 2, maybe it's 3, we can actually solve this still by factorization. More than 3, we don't have any general method. We have, but very complicated, 3, even 4, well, 5. So the only way is we have to solve this equation by factorization method. If you don't practice some questions, actually, you'll be not in trouble. Let's say you may be in difficult situation, because it really takes a long time to find the roots of this polynomial equation. Okay, now let's summarize and get back to solving problems. So if you're given n by n matrix A, so now we are talking about that eigenvalue problem. That everything is just solving this problem. What is it? That A times X vector, that's equal to lambda times X. It's a kind of linear transformation that transforms this vector X on its another vector which is parallel to itself. So we need to first compute a characteristic polynomial, that determinant of A minus lambda I, And after that, we need to find the eigenvalues of A by solving this equation, that characteristic equation. And for each eigenvalue, lambda, then we need to find the null space of the matrix A minus lambda I, right? So we need to solve this one. And after that, this is the eigenspace E lambda, the non-zero vectors of which are the eigenvectors of A corresponding to lambda. And after that, we should find a basis for each eigenspace. So we have to go through these 4 steps actually to deal with this kind of eigenvalue problem. And for 2 by 2, as I told you, is fine, but 3 by 3, it's not so sure. It takes time. So if you don't practice, even actually looking at the solution, if everything is given, you have to compute, so it takes time. Let's solve these 2 questions here. So find the eigenvalues and the corresponding eigenspaces of matrix A and matrix B. Yeah, we are given 2 matrices. And let's start with matrix A. To do this one, again, first we need to write our eigenvalue, what is it? Characteristic polynomial of this matrix A. So that is determinant of A minus lambda I, right? And here, if you just subtract this lambda from all the entries in the main diagonal, 0 minus lambda, here we have 0 minus lambda, 0 minus lambda, so here we have minus lambda, and 4 minus lambda, here we have 4 minus lambda. As you know, to actually compute the determinant, first we have to check actually which column or row contains the most number of zeros. Actually here, the first column contains 1 0, the first row contains 1 0. It doesn't matter, but either we can compute this determinant by cofactor expansion along the first column or along the first row. Let me just do this by along the first row, the first column. So here, negative lambda, right? We should delete the first column and the first row. So here we have minus lambda. So here we have minus lambda 1, minus lambda 1, minus 5 for minus lambda, minus 5 for minus lambda. And this is 0, so we should just know that it's equal to 0. I don't have to even write this. And here we have plus, minus, so it is here again plus. Here we have 2. We should delete the first column and the third row. Here we have 1, 0, negative lambda 1. And we know how to evaluate actually 2 by 2 determinants or the matrices, the determinants of 2 by 2 matrices. Here, if you evaluate this, minus lambda, here we have minus lambda times 4 minus lambda, minus 1 times negative 5. And here plus 1 times 1 minus 0 times minus lambda. So if you just simplify this, and after that, we will get this polynomial here, right? And we know that to get the eigenvalues, now we have to solve this equation. What is this? That thing is equal to 0 here. So now, since on the both side I have minus, I can just ignore, not ignore actually, by multiplying both sides by negative 1, right? Actually, I can just eliminate this minus here. So we have to solve this equation then. Here we have lambda cubed minus 4 lambda squared plus 5 lambda minus 2. That is equal to 0. So now my first attempt is I try to solve this by factorization. And to solve this cubic equation, I don't know if you remember this, you must have learned this in pre-calculus at the high school. The factorization method, if it has integer rules, or let's say the roots are integer, then it must be one of the factors of this constant term. So let's see, we have negative 2. Here, I expect that the roots are either plus minus 1 or plus minus 2, one of the roots. If I just find one of the roots, and I can actually, by using factor theorem, I can reduce the degree of this polynomial, right? To, let's say, if I reduce this by 1, then we will get quadratic equation, and we have the general method how to solve quadratic equation. So here, immediately, if I just evaluate this mentally, if it is 1, for example, let me just check. Let's say I assume that lambda 1 equals 1. Does it work or not? Substitute here. 1. Here we have minus 4. That's 1 minus 4 is minus 3. And here we have 5 minus 3 minus 2. That's minus 5. That's equal to 0. Oh, that's good for us. So that means that here, that's that thing is, this one is P of lambda, right? So here we have P of 1. If you substitute here, it is 1 minus 4 plus 5 minus 2. 1 minus 4 plus 5 minus 2. So that's equal to -3 plus 5, it is +2, and -2, that's equal to 0. That means that now we got the first eigenvalue. The first eigenvalue is 1. So the question is, also you can find another one, just trying this, but that may take long time. Or instead of this one, let me just use this method. Since lambda 1 is equal to 1 root is this, then it should be divisible by, actually, this p of lambda. That means I can write it as lambda minus 1, because when it is 1, 1, that's equal to 0. And here I can write another polynomial. Let me just write here p1 of lambda. This p1 of lambda is a quadratic expression here. Now how can I get this? Just divide that thing, that p of lambda, by lambda minus 1. I get p1 of lambda. Okay, by just long division we can do this. Here we have lambda cubed minus 4 lambda squared plus 5 lambda minus 2, and divided by lambda minus 1. Okay, here, maybe I should write a bit longer. Lambda cube is divided by lambda. So here we have lambda squared and multiplied back. Here we have lambda cube minus lambda squared, and subtract here, that's equal to 0. Minus 4 minus 1, that's equal to minus 3 lambda squared. And bringing this down, plus 5 lambda. Divide by lambda, that is minus 3 lambda. Multiplied back, so here we have minus 3 lambda squared and plus 3 lambda. So if you subtract here, it is 0. 5 minus 3 is 2. 2 lambda, and bring this minus 2 down, minus 2. 2 lambda is divided by lambda is plus 2. Multiply by back. Multiply this 2 by lambda minus 1. 2 lambda minus 1, that's equal to 0. Okay, I should just stop here. Okay, all of the thing is, I'm just trying to show you here, this is how we find the other solutions of this. So now that means that here I can write it as lambda minus 1. And here we have lambda squared minus 3 lambda plus 2. And also I can factorize this, that's equal to lambda minus 2, lambda minus 1. So here we have lambda minus 1, lambda minus 2, right? So now I can just write all the eigenvectors, eigenvalues of this matrix. That is the first one, that's equal to 1, and the second one also is equal to 1, and the third one, that's equal to 2. Actually, this one appears twice. Now, actually, we'll give a special name. We call this algebraic multiplicity of this thing. This lambda is 2 because it appears twice in the solution of this equation. Anyway, we got this thing, right? Now, we need to substitute. It says that here, okay. Here, we need to substitute into this equation, and we need to find the null space of that thing, right? Now we need to find the null space of that system. A1, here we have 3 lambdas, and here we have x is equal to 0. We have another system, A minus this lambda 1 and lambda 2 is equal, same. So just one of them is enough. Now I'll show you how to find the vectors here. So here we have A minus lambda 3i. And here we have x is equal to 0. Now here we have two systems, two systems of linear equations. By solving the first one, we got the eigenvectors corresponding to lambda 1. And by solving the second system, we will obtain the eigenvectors corresponding to lambda 3. Okay. So now let's continue solving this. Let me move to the other slides. Actually, I just need this thing because for reference. Okay, let me just keep it here. Okay. So now our lambda 1 is 1. Also, let me draw one line so that's okay. I can see. Okay. So Now let's start with lambda 1. The first one is now lambda 1 is equal to 1. So now if we substitute this here, what we got here? Here we have this kind of system. Here we have, I'm not going to write the zero column here. Here we have negative 1, 1, 0, 0, negative 1, 1, 2, negative 5, and 4 minus 1, that's equal to 3. Actually, here we have 0, 0, 0, so I'm just not writing this to save time. And because all the operations on zeros, again, they create zeros, that's why we just keep in mind that here we have zero column here. And that is actually the coefficient matrix of our homogeneous system. What we have here? Here we have this system. Now we are solving a system, lambda 1I times x here, and we have here 0 vector. Okay. So now, immediately, if you reduce this to reduce to echelon form, negative 1 and 1, 0, 0, negative 1, 1. Let me multiply the first row by 2 and add it to the third row. Here we have negative 2 plus 2, that's equal to 0. And multiply by 2, it is 2 plus negative 5, that's equal to negative 3. And here we have nothing, so it's equal to 3. And now, as you see here, the third row is just the scalar multiple of the second row, right? If you just multiply by 3, we have negative 3, 3, 3. So, and multiply the second row by 3 and add it to the third row, we got zeros here. And also add actually the second row to the first row. What we got here? Here we have minus 1, 0, 1. Here we have 0, minus 1, 1, 0, 0, 0. And also I can multiply because I want my pivots to be 1. So I can just multiply the first row by minus. Then we'll have here 1 minus 1. And also similar way, if you multiply the second row by negative 1, here we have 1, and here we have negative 1. So now if you just write the corresponding system, what we got here? Here we have x1 minus x3, that's equal to 0. And the second row, here we have x1, sorry, it's not x1, it is x2 minus x3, that is equal to 0, right? So from here, we got x1 equals x3, and x2 is equal to x3. What does it mean? x1 equals x3, x3 equals x2. That means that also actually we can conclude that also this x1 is equal to x2 is equal to x3. And let's say this x3 is s, okay? And what we got here? Here we have then this eigenvector corresponding to this will be, here we have just, I can just take only one, okay, because when you're writing eigenspace, I can include all. So here we are talking about this vector, right? Here we have S, 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 because here x1 equals x2, x2 equals x3, and if you just take this x1 to x1, x2, x3 as S, here we have S, S, S. So here we have one of these vectors actually. It is 1, 1, 1. All right. So now we can just write the eigenspace corresponding to this eigenvalue. Then here our eigenspace is, what is it? It's just span of these vectors, 1, 1, and 1. That is our eigenspace. And what was the question? Remember, the question was find the eigenvalues. Okay, we got it already. And the corresponding eigenspaces of matrix A and the matrix B. So that is the eigenspace corresponding to, the eigenspace of this lambda 1. Now the second case is, the second one is, what is our lambda 2? If you remember, that is what we got here, 2, right? So here we have lambda 2 is equal to 2. So now again, if you just substitute here, what we got here? Here we have our matrix. Here we have minus 2, minus 2, 1, 0, 0, minus 2, 1, 2, minus 5, 4, minus 2, that's equal to 2, right? And here we have negative 2, 1, 0, 0, negative 2, 1. And if you just add the first row to the third row, minus 2 plus 2, that's 0. 1 plus negative 5, that's minus 4. 0 plus 2, it is 2. Again, as you see here, if you just multiply the second row by negative 2 and add it to the third row, because we always must have this 1, 0 row. Otherwise, we'll not have non-zero solution here. Minus 2, 1, 0, 0, minus 2, 1, and here we have 0, 0, 0. Okay. So one more, since I'm trying to reduce this to reduced row echelon form, multiply the first row by negative 1 over 2. So here we have 1 minus 1 over 2, 0. And here we have 0 multiplied by minus 1 over 2, 1 minus 1 over 2, 0, 0, 0. Okay, one more, and multiply the second row by half, 1 over 2, and add it to the first row. Here we have 1, 0, multiplied by half, that is minus 1 over 4. So here we have minus 1 over 4. Here we have 0, and here we have 1 minus 1 over 2, 0, 0, 0. Okay, so now we can just write the corresponding the system here. So here we have x1 minus 1 over 4 x3, that's equal to 0. And here we have x2 minus 1 over 2 x3, that's equal to 0. So here we have one variable. So I can just take this x3. Let me take s, since here we have 4 and 2, the common denominator is 4. I can just take it as 4t. Okay. So at the time, what we have here? So here, from here, x1 equals 1 over 4 x3, which is equal to, if you substitute here, 4t times 1 over 4, that's equal to just t. And here, x2 is equal to 1 over 2 x3, which is equal to 2t. Then our x is, what is it? Actually, one of these vectors. Here we have x1 is x1, x2, x3. That is, here we have x1 is t, x2 is 2t, and x3 is 4t. Right? Eigenvectors. Here we have t, here we have 1, 2, 4. Actually, 1 to 4, one of the eigenvectors here. Now we can just write the eigenspace of this eigenvalue, that is 2. The eigenspace is just the span of these vectors. It is 1, 2, 4. Okay. As matrix B, I will leave it for you. So here in the question, you notice that one appeared twice. So we call this that algebraic multiplicity. Now we have two different concepts here. Sometimes the solution may appear more than once. So algebraic multiplicity of an eigenvalue is defined to be its multiplicity as a root of the characteristic equation. That means that one root appears how many times? Like as you see here, one appears twice, right? Lambda 1 equals 1, lambda 2 equals 1. So algebraic multiplicity of that eigenvalue is 2 because it appears 2. And geometric multiplicity of an eigenvalue is defined to be as a dimension of its corresponding eigenspace. So geometry multiplicity of an eigenvalue. In the previous example, for example, in the first one, and here, right, it appears, and how many vectors? It says the dimension of its corresponding eigenspace. So this corresponding eigenspace, it has only one vector. So this geometry multiplicity is 1. And here, the geometric multiplicity of 2 is 1. And how about the algebraic multiplicity of eigenvalue 1? That is 2 because it appears 2. And here, algebraic multiplicity of 2 is only 1 because it appears 1. Okay. So the eigenvalues of a triangular matrix are the entries on its main diagonal. Why? Because here it's a lower triangular matrix here, right? And here, if you just multiply A minus lambda I, for example, what do we got here? We got here matrix 7 minus lambda 0, 0, 0, negative 1 minus 1 minus lambda 0, 0, 5, 9, 3 minus lambda, here we have 0, and 1, 4 minus 5, 2 minus lambda, right? Actually, we know how to calculate this determinant. So here, this P of lambda will be 7 minus lambda times minus 1 minus lambda times 3 minus lambda times 2 minus lambda. It's already factorized, right? If you just solve this, then lambda 1 equals, the first one is 7, lambda 2 equals negative 1, which is the second entry in the main diagonal, and the lambda 3 equals 3, because 3 minus 3 is equal to 0. That's the third one, and the lambda 4 is equal to 2. That theorem says about this. So to find the eigenvalues of the matrix, so these are the eigenvalues of this matrix if the matrix is upper triangular or lower triangular matrix. All right. Here we have one theorem. A square matrix is invertible if and only if 0 is not an eigenvalue of A. So that means that if 0 is an eigenvalue of A, then it is not invertible, right? If it is invertible, then 0 does not appear as an eigenvalue of our problem. So the question is quite easy. I mean, the proof is very simple. So if A is invertible, we know that it's invertible if and only if, we know that A is invertible, right? If and only if, this IFF means if and only if, determinant of A is not equal to 0. So which means that actually it is equivalent to this, determinant of A minus 0 times lambda, right? So that's equal to, that's not equal to 0, right? So which says that 0 is not a root of the characteristic equation of A. So that means that 0 is not an eigenvalue of A. Anyway, I will finish today's class with the fundamental theorem of invertible matrices, version 3. Now we can add 2-3 more properties here. And actually, you are familiar with this. And we have some facts here. If one is true fact, then all of these facts are true. If one is wrong, none of them is true here. You're familiar with the first one. It contains 5, and after that, we added 5 or 6 more. 6 more, I think. So if A is invertible, let's say, suppose that A is invertible, then all of these facts are true. AX equals B has a unique solution for every B in Rm. AX equals 0 has only the trivial solution. That means the only solution is 0 solution. The reduced echelon form of A is IM. A is a product of elementary matrices. That we actually did this in the first part, in the version 1. And 2, we added these things. Then rank of A is equal to N. We already proved this. And nullity of A is also equal to 0. The column vectors of A are linearly independent. The column vectors of A span Rn. The column vectors of A form a basis for Rn. The row vectors of A are linearly independent. And row vectors of A span Rn. And row vectors of A form a basis for Rn. So now we are going to add 2 more things here. So we know that now determinant of A is not equal to 0. Why? Because it's not invertible, right? So if it is invertible, then determinant of A is not equal to 0. We already proved this. And one more thing is that 0 is not an eigenvalue of A. Okay, that is the version 3, that fundamental theorem of algebra. Guys, I will finish this video here. That's enough for today.